Okay, so after discussing some of the important items going to our practical use and design, let us summarize the principles involved and let us give a specific example that are being experienced, encountered on the ground. So let us start here with the design principles, starting with the foundation. A safe house must have a strong foundation, of course. The ground under the building has to bear the weight of the house. That is what we call load. Okay. The load on the ground for which the building is set or designed to be put up must be able to handle the weight of the total house, the total weight of the house to be constructed above it. It is a weak soil, the foundation must be made stronger. Okay, so that's why a particular engineering plan cannot be used on your neighbor because it is very specific on your place. Okay, so if the house has more than one floor, the foundation must also be made stronger. Foundations are best when continuous under the house. So the physical representation of our foundation is the what? The footings, because we are actually studying the building. But if you are a geodetic engineer, which is a specialty of civil engineering, included in the footing is the design of what? Of the soil in direct contact with the footings. Okay? That is also called foundation. The geotechnical, rather, geotechnical, not geodetic, geotechnical engineer must design the soil for which the footing must be put into it. Okay? So this is one principle of design. So if the soil is weak, this geotechnical engineer must make it stronger. Okay? So is the building built on sand, rock, or clay? So there is a what? Soil analysis. Another geotechnical principle. Okay? We have to design the foundation appropriately. So in this case, we are talking about the soil, not the footings. Okay? We have to design the soil appropriately. Okay? So that the soil is appropriate to the type of building that must be or decide to be constructed on above it. Okay. Next principle is soil for a good foundation that can carry the weight of a house must be well drained so that it is dry and not waterlogged. Okay. Very good principle, particularly it must be implemented during the construction. So well must be well drained. Okay. So let us make it bigger, okay? So must be well drained. So it is a weak foundation, a weak footings if the soil is what? Wet, okay? Because of so much water lag, okay? Waterlogged soil can become liquefied in an earthquake, okay? This is usually happening. If there is an earthquake, the soil will liquefy, okay? Turn into semi-liquid. So we already know what do we mean by semi-liquid. That is the technical term from geotechnical. Geotechnical. So that structure sink into the ground. It will what? So we are actually computing how much sinkage or how much the ground will what? Will drop from its original height or yes, well, height with respect to the your house, no? So if the soil is sinking little by little every year, what will happen after 5 years? What will happen after 10 years, right? So, okay, let us take a look at specific samples. Okay, so we have here a very small residential construction. Okay, so we have what? columns, and we have wall. Or supposed to be, this is supposed to be a tie beam, but since we are economizing on our cost, okay? So instead of tie beam, we are doing it with hollow blocks, okay? Wall, okay? So we have a proper how many? So there are about five columns. 1, 2, 3, 4, and 1 at the corner. Okay, so 5. So what can you say about this? Okay, that is an example of bad foundation. This house is being built in a swampy waterlogged area. That is what we call waterlogged. Okay, if you look at this one, the waterlogged. This is what we call waterlogged. Okay, waterlogged. Wet soil. So it must be dried before we can proceed. But anyway, in reality, what we are doing in construction, okay, we are just proceeding as if this waterlog doesn't happen. We are just proceeding normally, but it must not be the case. That is what? An example of bad foundation. Okay. As the foundation in foundation trench was dug, it filled with water, so the builders dropped dry sand and cement into it, and then the first row of blocks were located on top of this mixture. Okay. So this foundation in permanently wet soil are inadequate and will also be weak when impacted by an external hazard. So if the foundation is like that, meaning to say our result, the building or the residential building will become weak, okay, because its foundation is weak. So next, actual picture. Okay, so we have what? Body water, no? Bodies of water very near our, our constructed structure. So that is also a bad example of location. So we have to choose a location, but we cannot do it if that is really our property. That's why actually in bodies of water, there is no land title. About 5 to 10 meters, okay, from the body of water, there is no title. There's no land title. Okay? Because there must not be any residential area that must be constructed in that. But because there is no land title, what we are doing is we are claiming it to be ours. Okay? We are claiming, and then we are actually building our house there because there is no one who owns the area. There is no one who owns the area, but that is owned by the government. That is owned by the government. If there is no title, there is no land title, that is owned by the government. This house is located on a riverbed close to running water, where it's very vulnerable to flooding. Not only the house, but also its contents are vulnerable to destruction due to heavy rains. Houses should not be built in such obviously vulnerable location. If or they are, they should be designed to resist the hazards of location. So, just like what I've said, you can ask the engineer to design whatever your requirements might be. Okay, another actual picture. Okay, can you say about this? So this is an example of bad foundation. Bad foundation. Okay, so settlement. So the sinkage, they are putting sinks, but the sinkage is what? Uneven, not equal. Okay, uneven meaning the building sinks greater on one side than on the other side. That's why it it leans. Okay, it leans on one side. Okay, so that is an example of liquefaction. Because of liquefaction, the strength of the soil will decrease, and therefore the structure will experience a major hazard. So that is now useless. That structure is now useless. You cannot stay or occupy the house. The government or the city or the municipality will not give you occupancy permit for that house anymore. Okay, that is one reason that really it is required for the government official or city engineer or city inspector or engineering inspector to really visit the site, inspect. Okay, okay, so that you can see before you approve the for example occupancy permit, if it is a hazardous situation. Okay, the house was structurally good, but the foundation were poor. Look at the house. It is still not broken down into several pieces. It is still a single unit. It's still a frame with the walls and flooring, but it is tilted on one side, leaning on one side due to a major earthquake. So the soil experienced liquefaction. And of course, this is now a costly mistake. Okay, so it's very hard to do that. No? It's a costly mistake. Design principle, major topic number 2. So we are through with what? Foundation. So principle for the building that needs a coherent structure. If the structure is coherent and strong, it protects the whole house. Okay, so we are through with the discussion on simple foundation. Okay, what do you mean again by foundation? It means the footings when you are talking about building, and if you are a geotechnical engineer, the soil beneath the footings. Okay. Okay. So in this major principle, design principle number 2, we will look at a regular structure and integrated structural ring beam around tops of doors and windows connected to columns. We will look into it. And also an integrated structural ring beam around top of walls connected to columns. So we'll look into it. And triangular gable end walls, we will look into it. Okay, so let's proceed. Okay, so this is an example of a completed building. Okay, so look at the roof. Okay, triangular gable. We have columns, circular column here. Okay, look at this column here going straight down to the soil. And also here, circular column. Okay, another column here. Okay, so we have what? Wall and another column. Okay, so there are plenty of another column here. Here. So there are plenty of columns here. Columns, okay. So those are the location of columns, okay. And columns to columns, we will connect those by beam. So this is a good example. Regularly structured building which is able to withstand the impact of hazard. Notice the structure of columns and floors which are all joined to each other in a regular format. Okay? Overhanging parts of the building are well supported by continuous columns. So that's what I've shown. No? So this is a overhang or cantilever. This is a cantilever supposed to be, but that is only an overhang because it is not a real cantilever because it is supported by column at the end. Okay? Probably a small portion. Probably a small portion here is a cantilever, but majority is supported by a column. And it's good that this is slab and beam. No, you can see what the part wherein the beam runs. Okay, so we have a beam. So like here, no, we have a beam from this column to that column. Okay, we have a beam. Oh, we have a beam to that. So it is connected, well connected. So we have a beam here connecting this column to another column. We have a beam. So we can see the beam to beam construction which connect column to another column. Okay, and with the slab, flooring, and roofings connected properly in a standard format. This is a standard connection. This is one example, a very good example of one type of frame. So building framing, this is a good building framing. So let's look another example. This is just engineering plan. Okay, engineering plan. So you have what? Triangular gable. So you have what? Timber or framing on the roof, but you have beam here that is concrete. So beam. So we have beam on the flooring level. Flooring level. We have beam here and beam here. Beam support here. Beam support. So I think this is a very good framing plan, framing structure. It's a good framing structure. So because of that, this illustrates good structural design for a hollow block or brick wall building with a reinforced concrete structure. So hollow block, wallings, but we have what? Structural columns, structural beams, structural slab. Okay, a complete structural frame around the building is tied into the foundation. Okay, which one is those? Oh, this one. This is what we call tied beam because it tied the column on or about the flooring level, ground floor level, on the ground floor level. Okay, that is called the tied beam. So this is also called tied beam, but there are a specific name to it. So this is a tied beam. Sa tie beam because they tie the column, okay, properly, tying all the columns. So they are very important. Look, there is a tie beam, but about 1 to 1.5 meters, there's another tie beam here. Okay, it is a good design. This tie beam is to support the doors and windows later on. So there are windows here. So this tie beam will support those. Okay. If not, what we are actually doing is in real design, there is no tie beam here. Only tie beam on the floor level and tie beam on the what? On the roofing level. Okay. But here they are just what? Doing the lintel beam and lintel beam on the windows and doors. But it is better to have what? A tie beam on that level also. Okay. So that is what you have to expect when we are going to design. Those are the parts and components. The top of the wall is also tied together with the column by a second reinforced concrete ring beam. That is what we call ring beam. Tie beam or ring beam. But in our engineering plan, those are specified as tied beam. No? Tied beam. And the end walls are strengthened. Okay? It strengthens the end walls. Okay? Which are the end walls? These are the end walls. And you can put up another hollow block, series of hollow blocks here. Okay, like this. Okay, like at the back here, there is a series of hollow blocks after the tie beam on the roofing level. So we have also series of hollow blocks around here. Okay, but we have what support. We have a proper support on that gable, triangular gable. Okay, so another example here. So what can you say? Is this a good example or not? So we have what? Column in front, column framing for the building itself. We have tie beam, ground level. We have tie beam here at the top. Okay. We have broken tie beam on the door and window level, but we have a proper tie beam at the top. So it doesn't matter. This is still good because it could be here so that we can have a complete ring beam, but still good. However, okay, brick. This is a brick, not a hollow block. No, so this is a brick walling. So this again another good example. Even though there is a broken tie beam or ring beam. Okay, so this is a well-structured house that follows all the above design principle. Notice the good foundation, the good structural framing of the building, and the two ring beams connecting all the, so minimum two. So if there are three, it's better. At the top of the doors and windows and at the top of the walls. At the top of the doors and windows, as I already shown, gable and walls are also strengthened with reinforced concrete. So the gables are also there. So which one are the gables? This is what we call the triangular gable. These are the triangular gable. It is supported by this beam. Okay, and then later on it will have what extension of the column. Okay, so this is the triangular gable. Okay. So next picture, actual. So this is a bad example. You cannot see a column. There is no column at the corner. There is no tie beam. There's no tie beam. Okay? So there's no column. Okay? So susceptible to environment. Okay? There's no tie beam on the triangular gable. So there's no support. There is no extension of, so there is no column beam. Only walls. No? And roof. Okay? This is a bad example of structure. This house has no structural column. There's no structural column. And no ring beams to hold the structure together. There are no columns at the corners or within the walls. And there are no ring beams at the top of doors and windows or at the top of the walls. This building will have little resistance to being destroyed by any impact from nature. Normal environmental condition, this will what? Be destroyed. What more if we are looking at what? Earthquake or storm. Okay. We are looking at here at the normal strength of storm and normal intensity of earthquake. What do we mean by normal? That is written on the code. What is within? That is the within maximum intensity that our building could stand. We can choose that in our design specification, in our code. Okay. Another example. Okay. A very bad example. Because you can see there is what? A single column here, but you can see this is what we call honeycomb. No? Honeycomb, this one. No? Honeycomb. The column is actually plastered. I think it is plastered. It is not what? Poured. The column is not poured without what? Formworks. Okay? It's just being plastered. Okay. I don't think there is no other column. This is the only one. Maybe there are others, but very limited amount of column. As you can see, there is no supporting column here. There's no beam. Okay, so only hollow blocks. Okay, another bad example of structuring of a house. The columns are very poor. When concrete poured in stages after the walls are built up, the concrete has not fully covered the steel, so that reinforcing will rust. So the steel will immediately rust. Okay, because it is open at some areas. No, the columns are too small and the steel is too close together. Okay, look at that. So imagine here, column, steel bars. The width of the column may be from this point to this point, but the steel bars are very close together. Okay, so those are the things that we need to understand. We need to recall during our computation, okay, and specifying the design. Okay, the concrete was not tamped to ensure good compaction. Okay, so there's no vibrator. Okay, so during pouring of concrete, there are vibrators for medium rise, high rise building. But if small residential unit, you just need what? Tamping. You just need tamp, meaning in our local dialect, puk 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 lang, ano? Puk puk puk, ano? So tamping, okay? So we just need tamping. Columns should not be made to fit within the thickness of the wall because there is not enough room to properly cover the column reinforcement with concrete. You will understand this better during our actual analysis and design. This kind of column does little to give a house structural strength. It would have been better to have a proper column at the end of the wall on the right. Okay, end of the wall on the right. What do you mean? So column here, okay, here in this area, rather than here. Okay, so those are some of the principles. Okay, insufficient amount of column. There are only 1 and 2, and you have what? Single beam here. Okay, so very bad example again of structure. Okay, not good structure. Another example of house which has too little structure to brace the walls against lateral forces. So who will support the lateral forces? Columns, beams. Okay, those are needed. This is a common construction fault with hollow blocks. Columns are inadequate, too small, and poorly constructed. And there should be a reinforced column between the door and window. So the windows and doors have inadequate structural support. When the forces of nature strike this house, it will progressively deteriorate. Only wind load could deteriorate this type of structure. Okay, next. So is this good or bad? Okay, proper beam at the top. Beam, cord of the roof. Roofing cord, we have what? Column, which extend up to the roofing. Another column, another column. Okay, we have additional support here. Okay, we have additional support here. So we have good column. Okay, so it's good, no? It's better